Hello there, Mr. Sutton here, bringing you the AB Calculus 415 Extra Practice Number 2 solutions on advanced related rates. For this problem, we have a sand and gravel plant with sand falling off a conveyor belt into a conical pile at a rate of 10 cubic feet per minute. So this is a change in volume, and the diameter of the base of this pile is approximately 3 times the height. We want to know the rate at which the height of the pile is changing when the pile is 15 feet high. So we're asking for one rate of change. They're giving us another rate of change. This is a related rates problem. So that tells us that we need to find an equation that ties all these quantities together, take the derivative with respect to time, and then solve for the rate of time that we're looking for. So a good formula to use here would be the one they gave us, the volume of a cone, because we have a change in volume and we're asking about a change in height. So let me just rewrite that a little bit clearer here. And here's an issue, though. So they're talking about the change in height, and they give us a height, so that's good. But they didn't really give us much about the radius. In fact, they didn't tell us anything about the radius. They said the diameter is 3 times the height, so that's at least a starting point. But it would be a good idea to, since we don't know much about the radius, maybe try to express it in terms of the height and get rid of the r. And also, I mean, honestly, this is going to be a product rule, which isn't great to deal with either. So let's start with this idea that the diameter is 3 times the height. So I'm going to write d equals 3h. Now diameter is really 2 times the radius. So now I can write 2r equals 3h. And at this point I'm going to isolate r so that I can swap out this r for an expression that has h's in it. So I can write r equals 3/2 h. And this now gives me something I can replace the r with in the original equation. So let me go ahead and do that. I'm going to write volume equals 1/3 pi times 3/2 h quantity squared. And at this point, it's time to clean this up a little bit. So if I square this, this is going to be 9/4 h squared. 9/4 times 1/3, that's going to be 9/12, which is 3/4. So we have 3/4 pi. And we also have an h squared times an h, which is going to give me h to the 3rd power. There we are, h to the 3rd. So now that we've got an equation with only h's in it, I mean, that's at least going to help us. Let's go ahead and take the derivative with respect to time. And by the way, I could have taken the derivative back here. I just would have had a tougher time dealing with all these r values. I would have had to have used this equation to solve for r and also dr over dt while I was at it. But this is a little easier to deal with. So we have dv over dt equals, using the power rule over here, this is going to be 9/4 pi h squared times dh over dt. Everything is a function of time. And eventually I want to solve for the rate at which the height is changing, so dh over dt. That means I have to plug things in for dv over dt and h. So for dv over dt, that's the rate of change of volume that they gave us up here. Our conical pile is growing at 10 cubic feet per minute, so I'll plug in 10 for dv over dt. And for the h here, that's the height at the exact moment in time that we care about, and they said that that height was 15 feet. That's a pretty tall pile. So we have 9/4 pi times 15 squared dh over dt. And we still have the dh over dt there, because we haven't solved for it just yet. We haven't found out what it is just yet. Now let's go ahead and, honestly, I'm just going to divide both sides by this whole bunch of stuff next to the dh over dt, and that'll give me my answer. I'm going to do this on the calculator now. So here I am on the calculator. Probably the easiest way to divide this is by using my fancy fraction mode, alpha y equals. So plugging that in, that comes out to 0.006. Now, what's the units going to be on this? dh over dt is what we just solved for here. H, the height, is measured in feet, and t, the time, that's measured in minutes. So this is going to be 0.006 feet per minute that the height is changing at. On this one, the base of a triangle is increasing at a certain rate, and the area's got another rate of increase. We want to know the rate at which the height of this triangle is changing when base is 5 and the area is 50. So we've got multiple rates of change going on. This is going to be one of those related rates problems. We're going to have to find an equation that ties everything together and differentiate with respect to time to get at these rates of change. Probably the best formula to use, since we're talking about triangle area, is going to be the area formula, A equals 1/2 base times height. So I'm going to go ahead and just differentiate this all with respect to time. Derivative of A, that's going to be dA over dt. To take the derivative of the right side, I'm going to need to use the product rule. So let me get out the box and ribbon for that. So I have 1/2 times b for one of my factors. H is going to be my other factor. Derivatives of those are going to be 1/2 dB over dt, because base is a function of time, and also dH over dt is the other one. Using the ribbon to multiply this out, I've got 1/2 h dB over dt plus 1/2 b dH over dt. And ultimately, I'm going to be solving for the rate that the height is changing. That's dH over dt. So I need to make sure I have something to plug in for the other four things here. So going from left to right, dA over dt, that's the change in area, which they said was 4 centimeters squared per minute. So we'll put a 4 in for dA over dt. For h, well, they gave us the height. Well, actually, no, they didn't. They gave us the base, but not the height. So we're going to have to go back and solve for the height. But they did give us the base. They gave us the area. So if you have the base and the area, you can use the original equation here to solve for the height. So I can write that 50, the area, equals 1/2 times my base of 5 times that unknown height. And now if I divide by 5, that's going to be 10 equals 1/2 h. So we multiply by 2 then. So h is going to be 20. So we can write 1/2 times 20, and dB over dt, that's the rate at which the base is changing. They said that that was 2 right here. And then we have 1/2 times the base, which they said was 5. And we're still looking for dH over dt. So let's go ahead and clean this up now and solve for dH over dt. So we've got 4. We've got, let's see, half of 20 is 10 times 2 is 20 again. And then we have half of 5, dH over dt. So I'm going to just do the rest of this on the calculator. I feel like I'll mess it up otherwise. So doing this in a few steps, I've got 4. And from that, I'm going to subtract 20 to isolate the dH term. So minus 20 equals negative 16. Now I'm going to divide that by 5/2, which is really just 2.5. So dividing by 2.5, we end up with negative 6.4. And this is dH over dt. Height is measured in centimeters. Time is measured in minutes. So this is going to be negative 6.4 centimeters per minute. For this problem, we have the altitude of a triangle increasing at a certain rate and the area also increasing at a different rate. We want to know the speed the base of the triangle is changing at when our altitude is 3 centimeters and the area is 18. Since I have multiple rates of change involved here, this is a related rates type of setup. I need to write an equation that relates all of these and then take the derivative with respect to time. That'll help me use some of these rates of change and find others. So a good formula on this one, since we were talking about triangle area, would be the area formula, A equals 1/2 base times height. Let me go ahead and take the derivative of all of this with respect to time. So derivative of A then is going to be dA over dt. And on the right side of the equation here, we need to use the product rule. So let me get the box and ribbon ready here. So my factors are going to be, let's see, 1/2 b, h, and now I have to take their derivatives. So this will be 1/2 dB over dt and dH over dt. Using the ribbon to multiply that out, we've got 1/2 h dB over dt plus 1/2 b dH over dt. So ultimately, I'm solving for dH over dt because I want to know the, actually, no, I take that back, solving for dB over dt because we're saying what speed is the base of the triangle changing at. So we're going to solve for this, which means everything else better have some kind of number attached to it. dA over dt, they gave us that. The area is changing at a rate of 1 square centimeter per minute, so that's going to be a 1 right there. H, that's the height at a certain point in time. That's this 3 centimeters they gave us. dB over dt, we're just going to leave that there because we're solving for that. And over here, B, that's our base. Well, it turns out we don't know the base, but we can find it because we know the height of the triangle, we know the area, so we can use the original formula here to find the base. So we can write area 18 equals 1/2 times base times a height of 3. And then if I divide by 3, that's going to be 6 over there. Multiply by 2, we have b equals 12. So this is going to be plus 1/2 times 12. And dh over dt, did they give us that one? They did. The altitude of the triangle is increasing at a rate of 4 centimeters per minute. So 4, then that's the change in height with respect to time, and we'll put that in there. Okay, let's clean this up a little bit. So we're going to have 1 equals 3/2 dB over dt plus, let's see here, this is 6 times 4, so 24. And we can do a little bit more here. I'm just going to do this on the calculator, though. So first, let me do 2 minus, we're going to have to subtract 24 to get it over there. So subtract 24, that gives me negative 22. Let me now divide by 3/2, also known as 1.5. And that comes out to about negative 14.667. And the units on this, since we're talking about dB over dt, the base is measured in centimeters. Time is measured in minutes. This is going to be centimeters per minute. For this problem, we have a rocket rising up, and it's going 880 feet per second at the time that it's 4,000 feet up. So it's not necessarily going a constant speed. We want to know, given this, how fast is the camera to rocket distance changing at that moment. So we've got a camera down here taking a picture of the rocket, and we have this distance between the camera and the rocket that we want to figure out how fast is this distance changing. Okay, so we've got one rate of change, this camera to rocket distance rate of change. We also have the rate of change of the rocket with respect to the ground. This is going to be a related rates problem because we have multiple rates of change involved. So it'll help us if we can set up an equation that relates all of these quantities and then take the derivative with respect to time. That'll give us access to those different rates of change. So a good formula to use here, since we appear to have a right triangle, is the Pythagorean theorem. So we can write 3,000 squared plus y squared equals z squared. And then taking the derivative of all of this with respect to time, so everything is going to get a d something over dt tail here. Derivative of 3,000 squared is just 0 because that's a constant. Y squared, that's going to become 2y dy dt. And then z squared, that's going to become 2z dz over dt. So ultimately, we want to figure out how this distance, this hypotenuse distance is changing. So we're looking for dz over dt, which means we need to figure out what y, dy over dt, and z are for this problem. Okay, well, we already know what y is. It's this 4,000 feet up they gave us. And dy over dt, that's how fast y is changing. So that's this 880. So we have 2 times 4,000 times 880 equals, well, what's z? We don't quite know, but we could figure it out because we can just use the Pythagorean theorem to figure out the missing z value. We already know y, at least at a certain time. It's 4,000 at the time that we care about. So if we plug in 3,000, 4,000, and square all that and do our Pythagorean dance here, we can figure out z. So if I square those, square root them, and then we end up with, let's see here, well, this is just a 3, 4, 5 triangle. I mean, you could do this on the calculator, but it's going to come out to 5,000. So this ends up being 2 times 5,000 times dz over dt. And at this point, let's see, we can clean this up a little bit maybe. Then again, you're probably just better off going on the calculator because it's a calculator problem and dividing all the stuff over here by all the stuff over here. So let's go ahead and do that. So I'm going to end up with 2 times 4,000 times 880, the left side of the equation, divided by 2 times 5,000. I'm going to use my fancy fraction formatting here so I don't have to worry about PEMDAS when I have multiple things being multiplied in the denominator. And pressing enter comes out to a grand total of 704. Now, what's the units going to be? It's going to be the same as the rising units here, feet per second. So that's 704 feet per second. On this one, we have a 13-foot ladder leaning against a house when the base starts to slide away. of course the base is going to start to slide away. These calculus problems are always dangerous. By the time the base is 12 feet from the house, the base is moving at a rate of 5 feet per second. We want to know how fast the top of the ladder is sliding down the wall. And hopefully we don't have to calculate this while the ladder is sliding out from under us. So let me start by drawing a picture on this one. We've basically got a triangle going on, and it's not a static triangle. This triangle is constantly changing as this ladder falls. But one thing that is going to remain constant is this 13-foot ladder. So we've got an x value to tell us how far away the base of the ladder is from the house, the y value, how far away the top is from the ground, but then this hypotenuse here, this is going to be a constant value of 13. The ladder is not changing its length. All right, so because we've got multiple rates of change going on, we're talking about, they gave us the rate of change of x, and they want to know the rate of change of y. This is going to be a related rates problem. We need to write an equation that ties all this together, differentiate it with respect to time, and then figure out one rate of time by using another one. Well, let's start with the equation. Since we've got essentially a right triangle, this is going to be Pythagorean theorem time. So x squared plus y squared equals 13 squared. Taking the derivative of all this with respect to time, we've got 2x dx over dt plus 2y dy over dt, basically using the chain rule because x and y are inner functions of time. And then derivative of 13 squared, well, that's just 0 because 13 squared is a constant. So we're trying to find dy over dt in this one, how fast the ladder is sliding down the wall. And we're going to end up most likely with a negative number here because we're going down, so that's a decrease in y. But anyway, moving on with plugging things in, we need x dx over dt and the y value itself. We've got x. The ladder is 12 feet from the house, at least the base is. So this is going to be 2 times 12. dx over dt, that is the 5 feet per second that this x value is gaining at this point in time. And then y, well, we don't actually have y, but we can find it. At this particular point in time that the problem takes place at, we have an x value of 12. So we can actually use the Pythagorean theorem again to figure out the y value at that point in time. So I'm going to write 12 squared plus y squared equals 13 squared. And then y is just going to be the square root of 13 squared minus 12 squared. So that's 169 minus 144. Square root of 25 is going to give us 5. Or you might have just known, hey, this is a 5, 12, 13 triangle. Maybe you remembered that from your geometry days. Anywho, this is going to be 2 times 5. dy over dt is hanging around because that's what we're trying to solve for. And, you know, it looks like I could probably do this without a calculator. So let's see here. This is going to be 5 times 12 is going to be 60 times 2 is 120. We're going to subtract that over here and then divide that by, it looks like 10. So that's going to be negative 12. And this is going to be in units of, well, let's see here. Y is measured in feet. Time is measured in seconds. So this is negative 12 feet per second. For this problem, we have a boat being pulled into a dock by a rope that's attached to the bow of the boat and passing through a pulley on the dock 1 meter higher than the bow of the boat. So also 1 meter above the dock then. If the rope is pulled in at a rate of 1 meter per second, how fast is the boat approaching the dock when it's 8 meters from the dock? Okay, so let's draw this situation out. We've basically got a triangle here. If this is one of those where if you can visualize it, it's a lot easier. So we have a boat somewhere out here in the water. Here's the dock over here, and we're pulling this boat this way. So as we pull the boat in, this triangle is getting smaller. And now we also have a pulley up here. That's how we're actually getting the boat, some kind of physics leverage thing that I don't really know that much about. So let's label this triangle. We have the distance between the boat and the dock, which we'll call x. We have the distance between the dock and the pulley, which we know what that is. That's 1 meter. So we'll put 1 meter there. And then we have this other distance between the pulley and the boat, the bow of the boat, which we'll call z. So I'm given the rate of change of x, basically, and I want to know the rate of change of z. Actually, no, other way around. The rope's being pulled in at a certain rate, so I'm given the rate of change of z, and I want to know the rate of change of x. There we go. Anyway, we've got multiple rates of change. So this is a related rates problem. I need an equation that ties all of this together, and then I need to take the derivative with respect to time and plug things in and sort that out. So a good equation to use here, since we've got a triangle, Pythagorean theorem would help us out. This is going to be a right triangle. So we have x squared plus 1 squared equals z squared. And then taking the derivative of this with respect to time, we've got 2x times dx over dt, because x is a function of time. Derivative of 1 squared is going to be 0. Derivative of z squared, that's going to be 2z times dz over dt. And again, we're trying to figure out dx over dt, so this is the only thing we're not going to have a number to plug in. So that means x, we should have a number. We want to know how fast the boat's approaching the dock when it is 8 meters from the dock. So that's going to be 8. And dx over dt, we don't know yet. Z, that's the length of the rope, how much rope is out there, and we don't know that. They didn't tell us that. However, since we know that this x value at the point in time we care about in this problem, this x value is 8, and we already have this constant fixed value over here of 1, we can actually use the Pythagorean theorem to calculate the length of the rope at this point in time. So let me plug 8 in for x here. So we have 8 squared plus 1 squared equals z squared. And then at this one point in time, z is going to have a value of the square root of 8 squared plus 1 squared, also known as radical 65. We could get a decimal, but this is the exact value, so why mess with decimals until we have to? We'll do it at the end of the problem. All right, so this is going to be 2 times radical 65. And now dz over dt, did they at least tell us that? Well, they did. If the rope is pulled in at a rate of 1 meter per second. So that's going to be 1 for dz over dt. And at this point, I am just going to divide both sides by essentially 16 to get dx over dt by itself. So here we are. 2 radical 65 divided by 16 comes out to 1.008. And that is going to be, let's see here, because it's how fast the boat is approaching, it's got to have the same units of measurement as this other one-dimensional measure, so that's going to be meters per second. 1.008 meters per second.